Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about Bayesian models. The Bayesian framework for parametric modeling is extremely popular because it allows us to quantify our uncertainty about the parameters in our parametric models in a very principled way. It also allows us to incorporate prior information about those parameters. Let's take a look. We're going to talk about Bayesian models. Our goal is to describe the framework for Bayesian modeling. Remember that we already discussed the differences between non-parametric and parametric models. Here in this example, in case you don't remember, we were modeling the free throws shot by Kevin Durant. In particular, we were interested in the length of streaks of consecutive made free throws. We had this non-parametric model that was the empirical PMF, just computed from our data. And then we had this parametric model, which, if you remember, was essentially equivalent to a geometric random variable or a geometric parametric model. And the advantage was that the parametric model was making certain assumptions that enabled us to obtain a smoother fit to the data, whereas the non-parametric model was somewhat noisy. Okay, so we see the noise there. Now, in this video, we're going to talk about parametric models where we take a Bayesian viewpoint. Here, when we were fitting this parametric model to our data, essentially what we said is the parameter within the parametric model is a constant that we need to fit so that, or that we need to estimate so that the fit of the parametric model to the data is as good as possible. And the way we did that was through maximum likelihood. In the Bayesian framework, we take a different viewpoint where we interpret that parameter as a random variable. We're going to see how this works. So now within the Bayesian framework, we say that the parameters are random variables. This is why we see that squiggly line on top of the parameter, because now this is a random variable that we need to describe in terms of probabilities associated to it. Or using probability density function. If it's continuous, usually it's going to be continuous. Or if for some reason we decided it was discrete, we would use a PMF. Now we're going to model the data in terms of that random variable that represents the parameters in our model. So we have two decisions to make. We need to decide what is the distribution of our parameters before we see any data. We call that the prior distribution of the parameters. Typically, it's going to be a PDF because typically we're going to use continuous distributions to define our parameters. The other decision that we need to make is what is the conditional distribution or the likelihood of the data given the parameters. If we fix the parameters, what is the distribution of the data under our parametric model of interest? In traditional parametric modeling, we did not have this first decision. We just say, the parameters are going to be some constant that we're going to choose so that we get the best possible fit to the data. But we did have this part. We did have a likelihood. The key difference is that the likelihood did not have a probabilistic interpretation. It was just this function that enables us to choose the value of the parameters so that we get the best fit to the data. Our goal in Bayesian parametric modeling is to compute the posterior distribution of the parameters given the data, which we can see as updating this distribution once we have seen the data. How do we update our uncertainty about the parameters based on the data? We're going to take a close look at a very simple example that is going to show you the differences between traditional parametric modeling and Bayesian parametric modeling. So here we're going to model a single coin flip, okay? And our parameter of interest is going to be the probability of heads, the probability that when we flip the coin, it lands on heads. We call this parameter theta. In the traditional parametric modeling framework, this is just a constant, okay? Now, what is the likelihood of the data? Remember, the likelihood is the probability of observing the data when we fix a certain value of the parameters. So this way is a function of the parameters. In this case, we have a single coin flip. What's the probability of observing heads? Theta. So the likelihood if the flip is heads, is theta. Remember that the likelihood depends on the data that we observe. Here, the data is just a single data point that can be heads or tails. If we observe tails, what's the likelihood of observing that data? What's the probability of observing that data under the parametric model? It's 1 minus theta. All right? As simple as that. So now we want to estimate the parameter within the traditional parametric model. What do? We maximize the likelihood. Sometimes it's useful to draw the likelihood when you're trying to maximize it. So let me do that up here. So between the parameter lives between 0 and 1, those are the reasonable values for our parameter because it represents a probability. If the flip is heads, then the likelihood looks like that as a function of theta. What is the maximum likelihood estimate? It's equal to 1. That would be our maximum likelihood estimate. It's only a coin flip, right? Okay, so maximum likelihood estimate, if the flip is heads, our estimate is equal to 1. While you listen to that siren, I'm going to draw what the likelihood looks like if the flip is tails. If the flip is tails, then we have 1 minus theta that looks essentially like that. Okay, again from 0 to 1. So now if we maximize the likelihood, this is the likelihood with respect to theta, it's 0 if the flip is tails. All right, so this is what we would do in traditional parametric modeling. We choose the theta that best fits our data, and we leave it at that. Now let's apply Bayesian modeling to this same problem when we're flipping a single coin. Our parameter is again the probability of heads, but now it's not a constant. Okay, now it's a random variable, which is why it has this squiggly line on top. So now we have to worry about its distribution, not its specific value. We're going to have some prior distribution on the parameter. We will choose it in a moment. Then we need the likelihood. What is the likelihood? The likelihood is the conditional probability of the data given the parameter. Here we have discrete data because either we observe tails or we observe heads. So that's why the likelihood is a conditional PMF. In situations where we have continuous data, we would have a conditional PDF there. We're calling the data R here, which is the result of the coin flip. What is the probability that R is equal to 1 if we realize that here we're fixing the parameter of the coin? Well, the probability that R is equal to 1 is theta. What is the probability that R is equal to 0, that the coin flip is it's tails? If we fix theta, it's 1 minus theta. Notice that this likelihood is exactly the same as in the traditional parametric model, but it has a very different interpretation. Now it's a conditional probability. In the case of the parametric model, it's just a function that we maximize to find the value of the parameter that best fits the data. Great. What do we want when we're doing Bayesian modeling? We want the posterior. We want to update our uncertainty about the parameter theta given that we've seen the data. Okay, that's what we really want. In order to do that, we're going to have to choose a prior. Probably the simplest, most non-committal prior that we could think of is just saying, well, I think the parameter could be anywhere between 0 to 1 with constant density. Okay, using a uniform prior. So now let's derive the posterior under this uniform prior. And we're going to assume that the data that we observe is that the coin lands on tails. Now, based on this information, we're going to update our uncertainty about our parameter, about the probability that the coin is heads. So what is the posterior PDF? Well, let's make sure that we understand what we're talking about. Is the posterior PDF of the parameter given the data. Oops, not that. That looks a bit terrible. Given the data, when the data are equal to 0. So now we're going to apply the chain rule for discrete and continuous random variables. Remember that by the chain rule for discrete and continuous random variable, if we take the marginal PDF times the conditional PMF, this is the same as multiplying the marginal PMF times the conditional PDF. I hope I said that in the right direction. Okay, so now we can move this guy to divide and we get this formula. So now we just need to plug in the different values. What is this guy? That's the prior, it's uniform. So if theta is between 0 and 1, that's just equal to 1. What is this? This is the probability of observing tails given that the parameter is theta. So that's going to be 1 minus theta. Okay, that's why we have 1 minus theta times 1 up here. How are we going to compute this guy? We're going to write this proxy for the joint distribution between the continuous and the discrete random variables. We have discussed this in a previous video, and we're going to integrate out the continuous random variable. Equivalently, you can see this as basically taking this quantity here and normalizing it so that its integral is going to integrate to 1, right? This is exactly this quantity here that we're just integrating. When we divide by that, we ensure that the whole thing is going to integrate to 1. So what are we going to plug in here? We're going to plug 1 minus u, and here we're going to just plug 1. So we do that integral, and we get that the posterior PDF of the parameter giving this observation that the coin is tails is 2 times 1 minus theta. Let's take a look at how that looks. Take a look at how that looks. Wonderful. It's a triangle. It's a triangle that has moved in this direction, which kind of makes sense. So we start by saying, well, you know, we think that the parameter is we don't know what's going on with the parameter, so we assign it constant density within the unit interval. Oh, now we see that the coin was tails. The density moves to the left towards small values of small values of theta. That makes a lot of sense. What happens if we start with another density? So maybe we're, like betting on this coin flip with a friend, and we think the friend is going to deceive us. So we think there's a higher probability that the coin will land on heads. How do we update this uncertainty based on an observation that the coin actually landed on tails? We do exactly the same thing. We're going to compute the posterior PDF, but now starting at this prior PDF, where if you realize the PDF is equal to 2 theta between 0 and 1. So now when we apply exactly the same formula, where we're using the chain rule, and here we have the prior, here we have the likelihood, and then we normalize, now this guy is no longer going to be uniform, it's going to be equal to 2 theta. So we plug that in, the likelihood stays exactly the same. Down here, when we normalize, we have to normalize plugging in 2u there. Now we compute that integral, and we get that the new posterior is 6 theta times 1 minus theta. How does this look like? It looks like this. So this is kind of cool. We start kind of biased towards high values of theta, but then we see that the coin is tails. So then the density of the parameter shifts towards the left, but not as much as before because we start with this prior. This also incorporates our prior assumption that we think that the parameter is probably closer to 1. The Bayes framework allows you to do this in a principled way, but you do have to realize that your posterior can potentially be very influenced by the prior that you choose. A very popular distribution to model parameters that represent probabilities is the beta distribution. And in fact, these two distributions, the triangle and this inverted quadratic that we see there, both are beta distributions. The uniform is also a beta distribution. The triangle in the other direction is also a beta distribution. So what is a beta distribution? It's a unimodal prior. It's only going to have one maximum for parameters that represent probabilities. It looks like this. So essentially, let me walk you through it. This is just a normalizing factor that we're not going to worry about. But essentially, this is for values of the parameters between 0 and 1. It has one term that depends on the parameter a, that is a polynomial that grows towards 1. And then it has another term dependent on the parameter b, that is a polynomial that decays towards 1. So these two parameters are kind of fighting, and we're going to see the shapes that they produce when they fight. This is normalized by a beta function. That's not too important. This is just a normalization so that the PDF actually integrates to 1. So let's take a look. This is what happens if a is equal to 3 and b is equal to 2. Here a is kind of winning, so we see the distributions shifted towards 1. Here a is equal to 6, so even more shift. And here a is equal to 10, even more shift. Okay, so you see that if a is much larger than b, we get more density closer to 1. Here b is slightly larger than a, so the density shifts a bit towards 0. Here they're almost the same, so it's almost centered, but there's a slight shift towards 1. Here there's more shift towards 1. Here a lot of shift towards 0 because b is much larger than a. And here you can see that when b is larger, you get this shift towards 0. These are ways of representing our prior assumptions about a parameter that represents a probability, that is between 0 and 1. Now we're going to talk about what happens when we have more data points. And we will come back to the beta distribution in case you're wondering why did I bring it up. So you'll see in a moment. In our example with the coin flip, we had one single data point. That's not very satisfying. So what would happen if we had many coin flips? If we had many coin flips, now we have to make an assumption about their joint PMF, in particular their conditional joint PMF, given the parameter. A common assumption is that the data are conditionally independent once you fix the parameter. In terms of the likelihood, that this is completely equivalent to when we were doing maximum likelihood estimation under the assumption that the data were independent copies with the same parametric distribution with the same parameter. Okay, this is exactly equivalent. The consequence mathematically is that when we look at the conditional PMF, if the data are discrete, of the data given the parameter, it factorizes into a product of the conditional PMF of each data point given the same parameter. So we assume that the parameter is common to all of the data points, just as we did in traditional parametric modeling. The same thing if the data happen to be continuous, you have a conditional joint PDF of the data that factorizes into the product of the conditional PDFs of each data point given that parameter. So the parameter is fixed. Okay, we're assuming that all the data points come from the same parameter. Exactly like we did in traditional modeling under IID assumptions. Traditional parametric modeling. All right, so now we're going to consider a situation where we want to estimate the parameter of a Bernoulli random variable, given that we have a sequence, a data, basically, like, I don't know why I put sequence there. Basically, we have a set of outcomes that can be equal to 0 or 1. We want to aggregate them to estimate this parameter of the Bernoulli. We're going to have a parameter theta that is a random variable because we're within a Bayesian framework that is modeled as a beta distribution with parameters a and b. Now, what is the likelihood given a fixed value of the parameter of each data point? So each data point is going to be Bernoulli with parameter theta. So now we can think what is the likelihood of observing a certain number of ones. The likelihood of observing a certain number of ones is the same as the likelihood of n Bernoulli, independent Bernoulli random variables being equal to 1 if for each of them the parameter is equal to theta. I don't know if you hear the siren. Yeah, it's impossible to get complete silence in New York City. So I should have said that there we're making this conditional independence assumption. Now you definitely hear the siren. Hopefully everything's okay, but also hopefully the siren will leave us at some point, because I don't want to re-record this just because of the siren. So, take this time to digest a bit what we were talking about. Wow, like this, something must be happening. Okay, let's continue. Sorry about that. So what I was saying is that we have these conditional independence assumptions where these Bernoulli, these outcomes, are generated conditionally independent given the parameter. Okay, each is Bernoulli with parameter theta, where the parameter is fixed. Under that assumption, the number of ones, what is it? It's a binomial with parameters n and theta. Okay, well, this is the question that I wanted to ask you. What's the distribution of the number of ones if the data are conditionally independent given theta? In particular, given theta that is fixed to a certain constant. I would have asked you to think about it, but I was a bit distracted by the siren. It is what it is. This distribution is going to be binomial with parameters n and theta. Now, let's compute the posterior. Again, what do we want? We want the posterior of this parameter that represents a probability given x, which is the number of ones that we see out of these n Bernoulli outcomes. So we do what we always do. We write the PDF, the prior of the parameter, times the likelihood, and then we have to divide by this to normalize, and all this also comes from the chain rule. Now, what is this guy? It's a beta distribution with parameters a and b, which we will choose, right? What is this guy? It's a binomial distribution with parameters n and theta. And here, we're essentially going to integrate what we have in the numerator to ensure that things are normalized. So let's plug that in. This is what I'm talking about. We're basically just going to integrate what we have up in the numerator to ensure that things are normalized. Now we plug in, and let me walk you through this. The beta distribution, the beta distribution here, we plug in the binomial likelihood. Okay, and here we're integrating the same thing. So this is the binomial and this is the beta distribution. Notice that I haven't put the normalizing factor of the beta distribution because essentially it's the same here and here, so they just cancel out, and I didn't want to clutter this too much. We can actually also cancel out this term here because it's exactly the same in the numerator and the denominator. And now we can put things together, right? So we have theta to the power a minus 1 times theta to the power x. That's just theta to the power x plus a minus 1. We have 1 minus theta to the power b minus 1, 1 minus theta to the power n minus x. What's that? It's just 1 minus theta to the power n minus x plus b. Okay, and then we have a term here which is just normalizing this so that it's a valid PDF. What kind of PDF is this? If you remember from what I showed you before, this is just a beta. This is the PDF of a beta random variable where the parameters are x plus a and n minus x plus b. Remember that this first parameter pushes the density towards 1. So we have if we have a lot of ones in our data, this is going to push the density towards 1. This is the number of zeros, and this parameter pushes the density towards 0. So if we have a lot of zeros, the density is going to be pushed towards 0. We're going to see an example of this right now. In our example, first let's just make sure that we know what we have just proved, and then we will look at the example. So we have a sequence of n binary outcomes that can be 0 or 1. And the prior is beta with parameters a and b. And the likelihood is Bernoulli or equivalently binomial with parameters n and theta. Then what we have proved is that the posterior distribution is beta with parameters x plus a and n minus x plus b, where x is the number of ones that we observe in the data. This is very nice because we don't have to go through all of this pain of rederiving the posterior PDF each time we see data. It's always going to be a beta distribution, and we can very easily update the parameters. When this occurs, when we have a prior distribution and we apply a likelihood and the posterior belongs to the same family as the prior, we call this a conjugate prior for that likelihood. So the beta in statistics, in Bayesian statistics. So the beta distribution is a conjugate prior for the binomial likelihood. Now let's apply this to some real data. So here I gathered some data from a real poll in Pennsylvania, and I did this before the outcome of the election. As you might know, the outcome in Pennsylvania turned out to be critical. In the poll that I was looking at, 281 people intended to vote for Trump, 300 intended to vote for Biden. So let's think first what would happen if we applied traditional parametric modeling to this. So in traditional parametric modeling, what would we do? We would say, what's the parameter we're interested in? Let's say it's the fraction of Trump voters, theta. What is the maximum likelihood estimate? We already, under IID assumptions, here, let me pause for a moment. IID assumptions implies that we take all of Pennsylvania and we choose the people from the poll uniformly at random from all of Pennsylvania. Of course, that's not going to be correct, and you would have to correct for this, but this is just a cartoon example. So we're going to assume that we have these 581 people that are chosen completely uniformly at random from all of Pennsylvania. Of course, that's not the case. If it were, then the best estimate for the fraction of Trump voters that there are in Pennsylvania is 48.4%. What is the probability that Trump wins in Pennsylvania? I want you to think about this for a moment and really think about it, okay? Like, pause the video and think about it, because it's not as obvious as it may appear. You may be tempted to say that it's this probability, but that's really not correct. So what does this probability tell us? This probability, 48.4%, tells us the probability that if we pick anyone at random in Pennsylvania, they turn out to be a Trump voter. But that's not what we're asking, right? We're asking what is the probability that Trump wins in Pennsylvania. What does that probability refer to? What is the probability that the day of the election, more than half of the people vote for Trump? So if we're highly confident in this number, then this probability would be very small. And that typically happens in elections when you look at the probability that a Republican candidate wins in New York. Maybe the percentage of votes that they're going to get is like around 40%. But the probability that they win in New York is essentially zero, or like very, very small. Why? Because it's extremely unlikely, according to the model, that for some reason the day of the election, more than half of the people vote for the Republican in that state. Same thing in Alabama, right? In Alabama, you look at what's the fraction of Democrat voters. It might not be that small. It might be 40%. I'm making this up. The thing is that the probability that for some reason the voters that show up the day of the election, more than half of them are Democrats, is essentially zero. So that's why you will see probabilities that are extremely low for a Democrat winning in Alabama. So here we need to somehow define the probability that Trump wins in Pennsylvania. How can we do this within the traditional parametric model? I don't know. You can't, right? Because the traditional parametric model essentially just asks what is the parameter of the Bernoulli that best fits our data. What is the best parameter? This one. This is the best parameter that fits our data. We are not equipped to answer the question, what is the probability that the parameter for some reason is higher than 0.5, because the parameter is just a constant. We cannot answer this question about a constant. Here you can see the power of the Bayesian framework, because within the Bayesian framework, the parameter is a random variable. Okay, so now the fraction of Trump voters is a random variable. There's a certain uncertainty about the random variable that we're going to encode within our prior, and then we're going to update our uncertainty about that random variable based on the data, and we're going to compute the probability that that random variable is above 0.5. So this framework does enable us to answer the question, what is the probability that Trump will win Pennsylvania? So here we're going to have a certain prior. It's going to be very important how we choose that prior, as we will see in a moment. We're going to choose it to be beta with parameters A and B. How you choose the parameters A and B will depend on your prior beliefs. We're going to have a likelihood that is going to be binomial with parameters n and theta. Here we're making the same assumption as in the parametric modeling assumption, where we're imagining that we're choosing people completely at random from Pennsylvania. If we do that, each person that we pick is going to vote for Trump with a probability theta, where theta is the parameter. This is obviously an idealized assumption, but still, okay, we're within, you would have to correct for this in practice if you're doing the poll, for example, in an urban environment or not, etc. So under the assumptions that we're doing uniform sampling from all of Pennsylvania, we have a likelihood that is binomial with parameters n and theta. So what's the posterior going to be? We're in luck because the prior is beta and the prior is a conjugate prior with respect to the likelihood, to the binomial likelihood. The posterior is super easy to find. It's just going to be beta with parameters A plus 281 and B plus 300. Okay, that's all it is. So see that the number of Trump voters in the poll are pushing the density towards 1. The number of Biden voters is pushing the density towards 0 because we're modeling the probability of Trump, the fraction of Trump voters. What's the probability that Trump wins in Pennsylvania? How do we compute it from our posterior? Well, we want the probability that theta is bigger than 0.5 given that the data that we see. So what are we going to do? I didn't write it down explicitly, but I will. You take the posterior and you integrate it from 0.5 to 1. So now let's take a look at what happens for this data when we choose different values for A and B. For A equals 4 and B equals 6, which basically means this is the prior, this is what the beta distribution with A equals 4 and B equals 6 looks like. Here we think that Biden has higher chances, so this is why we start with a density that is more towards 0. When we apply when we update the prior and we compute the posterior, we get this beta distribution, and the black, this black area is the probability that the random variable that represents the fraction of Trump voters is above 0.5. In this case, it's 20%. So, non-negligible. What happens if we change the prior to be in the middle because we're not favoring either Biden or Trump? We get a pretty similar probability, but the probability increases, right? Because here we're favoring Biden. This is for parameters of the beta distribution that are equal to 5 and 5. What happens if we were favoring Trump? This probability is higher. Now we're going to see what happens if we were more certain in our prior. How do we become more certain? We increase the values of A and B so that the prior is more peaked. So for 40 and 60, the prior is more peaked. The probability, if we're favoring Biden with our prior, the probability that Trump wins suddenly becomes much smaller. If it's centered, it stays around like 20-something%. And if we're favoring Trump, suddenly the probabilities for Trump are obviously higher because we're more confident in our prior. What happens if we're extremely confident in our prior? Then we can essentially get whatever posterior we want, right? So if we're extremely confident that Biden is going to win, we start with a very peaked prior, that is to the left. The data are not able to shift it. They're not able to shift it enough. We get 100% that Biden wins. If it's really peaked at the middle, we get this probability. If it's very peaked towards Trump, even if it's close, we get that Trump wins 100%. So the probability that Trump wins is 100%. With this, I wanted to show you that the Bayesian framework is amazing because it allows us to answer the question, what is the probability that Trump wins, which we could not have answered within the parametric model, because within the traditional parametric framework, because in the traditional parametric framework, we only care about how do we fit this data, what's the value of the parameter that best fits the data. The Bayesian framework is great in that sense. It allows us to model the parameter with a distribution that incorporates uncertainty and enables us to answer questions regarding the probability that the parameter is in different ranges. It also allows us to incorporate prior information in a very flexible way. You have seen here like all the possible priors that we could have applied based on our assumptions on prior data, etc. But the bad news is that your posterior really depends on your prior. So you should not take probabilities that are computed within a Bayesian framework as the ultimate truth. Okay, they really depend on the prior that has been applied, and that's easy to forget sometimes when you just see a probability. Oh, the probability that Trump wins is whatever, 20%. This is really going to depend on the assumptions that go into the model, and it's very important to realize that. All right, what have we learned? We have learned about the Bayesian framework for parametric modeling. We have learned about conjugate priors, in particular, the beta distributions are conjugate prior for the likelihood. And we have applied these ideas to a real example that shows us both the advantages and the potential disadvantages of the Bayesian framework. Thank you very much.